so I am looking at the class chat. I'm going to try to follow that as I go along. And if you want to interact with everybody, use that Zoom class chat channel. As always, if you have a question and I'm just not seeing you in chat, feel free to unmute yourself and ask me. Tonight, we are going to follow the same schedule that we had on Monday, in that we're going to break at 7:45 Eastern, and then we're going to break at 8:45 Eastern. You got 15 minutes. Make sure you stand up, move your head around. Tonight we are talking about data and storage. And we are also going to be using Kahoot, but we're not going to use Kahoot until the end of class. So I've got a bunch of information to share with you in the beginning. Then by the time your brains are full, we'll have some fun and we'll game it with Kahoot. Tonight, specifically, the agenda is to discuss binary numbers, number representation, letter representation, voice representation, image and video representation, and then to dig a little deeper into bits and bytes. We start off talking about the binary number system. You can see the decimal image up there. In the decimal system that we use, we have 10 digits that everything is based on. And so in the decimal system, the whole numbers that are valid within each digit position range from 0 to 9. And I'll talk about digit position in a second. But the decimal system is also called base 10. So if you've ever heard of that term, that's what they're talking about. Versus binary, where there are only two numbers that you can use to represent values. So we've got the 10 digits versus in binary 2. And by that prefix, if you took Latin, of course, it represents 2. All right, so in our numbering system, in the base 10, we settled on 10 digits because the theory is we have 10 fingers. So you could count off all the digits on your fingers. But when we think in terms of computers, if we give them 10 different combinations to sift through, that's a lot of work for a computer. In our numbering system, you see numbers represented with, out of those 10 digits in each position here, so position 1, 2, 3, you can see any one of those 10 numbers, so 0 through 9. We also consider those positions in how we describe decimals. So there's the ones, tens, and hundredth position. You can see in the graphic on the screen, any value that is in the ones position, that is basically the number 1 times whatever that value is. So you can see 3 in the first position is a 3. Whenever you see a number in the tens position, that actually is that number multiplied by 10. So instead of this just being the number 2, it actually is representing the number 20. And of course, you add 20 to 3, and you get 23. And taking it further, you in the 100th position would multiply whatever that number is by 100. And so totaling out, you get 123. And that's how we represent decimal numbers. In the binary number system, you see it's a little different. We have the 1 position, we have the 2 position, but then that next position is 4. So just going back, 1, and then because we have a possibility of 10 numbers that we can use, it's tens. And then we have a possibility of 10 again. So we multiply 10 by 10, we get 100. And so you start to see this power of representation. So 1 times 10 is 10, 10 times 10 is 100. And that's how it came to be base 10, that we call that. But when you get to binary, because there's only 2, you have 1, and then you multiply that 2 and you get 2, and then you multiply 2 by 2 and you get 4. And so essentially, if we were to talk it out the way we talk about decimal, it'd be the 1s, 2s, 4s positions, but we don't explain it that way. The number on the screen in binary actually represents the number 0. When you take a look at this number, this is the number for 1. And the difference there is in any position that we have on the screen, instead of one of 10 numbers, again, you only have 1 or 0 to represent your value. So in the 1's position, you can have a 0, or you can have a 1, and then you run out of numbers to possibly use. And so when we get to the max number of numbers used, then if we're counting, we have to move into the 2nd position. And I have an example to show you there. So we went from 000 to 001. We ran out of combinations that we could use in that 1's spot. If we were to just have 000, we know that already is the number 0. So now we have to adjust in the 2nd position to the other value that we're allowed, and we put in a 1. And this particular binary representation is the number 2. So 0, flip your digit from 0 to 1, 1. Can't flip anymore, so now you need to move into the 2nd position. And because we've moved into this position, the next flip that we do, we kind of reset that 1's place, we go back to 0. And then we start incrementing after that 1 back to 1. I'm going to show you this in a little different representation. It's a little easier to see. So if you can see on the screen, I've got a spreadsheet. The way our numbers are, so we can start with 0. We can go to 1, 2, 3. And so these are all the possible ways we can represent our numbers 1 through 10, right? We can represent our digits, we'll say. But then once we've used all of our different digits in that 1's position, now we have to spread out to get another value, an increasing value. So that's when we start back at 0, but we move out to the 2nd position and we have 1 0, 1 1, 1 2, 1 3. You can see now we're going through that we've got the 1 in the 10's position and we're maintaining that it is 1. Then we are slowly incrementing through all of our 0 through 9 numbers after that 10's position. Let me get down to 15. So we have 0 through 9, and then once we run out of space, we go to our next position and we start over 0 through 9. We just add that 10's indicator. Binary is a little bit different because we only have the 2 values to choose from. So we have 0 and 1, and now we've run out of options for position 1, or our 1's position. So then we need to move out to the 2nd position. We need to start over and we're still going in that 0, 1, 0, 1, 0, 1, but in our second position there, now we have to add a 1. And again, we start 0. Now we keep that 1. We increment by 1. We've run out of options for that second position. Then we add in another 1. Again, starting at 0, we get 1, 0, 0, 1. After 100. After that, we've run out of 0, 1 combinations in the 1 position. Now we have to move to the second position, and we get 1, 1, 0. And then the other option there is 1, 1, 1. All right, so it keeps going, and you're flipping that switch from 1 to 0, 1 to 0. As you run out of options in a particular position and you move out, you keep then moving between 0 and 1. Again, we've run out of positions here, and we start over at 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So when we start thinking in terms of conversion, when the system is using binary, we can actually assign one of these decimal values to its equitable version in binary. So in binary, when it reads 1111, okay, Stephen, thank you. Hurts my brain too. It actually, we can convert that based on whatever application is running in the system. In our code, we can say when the system interprets a 1111, I want you to actually consider that 15, the value 15. And then we can build on that conversion more. And really why everything is based on this binary system is because it goes back to computers are very simple. They're processing very simple instruction, and it is a lot faster for them to interpret 1 or 0 versus having to go through and interpret, oh, what does 0 through 9 mean? And how many combinations of 0 through 9 can we possibly have? This machine code is much easier for the machine to work with. Will we ever have to actually figure this out? I'm going to go the route of calculators. When I was in school, we could not use calculators. Then I got into college and we could use a graphing calculator to get our answers. And I was like, finally, somebody had some common sense. So I would suggest to you to go out to the internet and Google for binary conversions. You're going to get nice big charts. The charts can also give you the same conversion values for some of the other storage concepts we're going to talk about tonight. All right. So again, this is 3, binary number for 3. And then this one is our binary number for 4, because again, we've done our 0, 1 flip-flop in the first position. We've done our 0, 1 flip-flop in the second position. And now we need to move out to the 4th position, what's considered the 4th position. And we need to start and flip that. Once we flip out the leftmost position, all of our other positions following that flip back to 0. And that's why you see that progression that we have in the spreadsheet. Once we bump out a position, all the following numbers reset to 0. All right, so if we're looking at our chart, we can see that we went from number 1, in the previous slide. We've reached the end. And so the next logical progression of numbers is we move to 1001. So in your mind, this may not look like, or you may not interpret it as 3. And this one, definitely when you read this, you probably think 11, but in binary, that's going to be 4. I messed that up. That's 3. That's 4. All right. So that's 3. That's 4. Going back to the slides, 011, 100. What number do we get when we see 1111?
7.
7. Because going back to this one, which was 4, the next progression we would be able to do is flip-flop this first position to 1. I wait 5. We run out of positions. We now have to go to the second position. This one gets flipped back to 0, and this is a 1. That one is going to be 6. Then we run out of possible combinations, and we get to start again at flipping both of these to 1111 or 111. And then because we're at 111, we have to bump out another position. What number do we get? Go ahead and write it in Pear Deck if we move to 1111. All right, I see a lot of 15s, and 15s is right. Now, I see a couple of 8s, and of course, if in our example, we were adding a decimal 1 to this number, we would, of course, have to carry the 1 over to the 4th position and flip all those following numbers back to 0. So yeah, you get 8. But if you are adding a 1 to this existing number in the next position, you get 15. So a couple different ways to interpret that. And it does get a little sticky because we think in terms of decimal, and the computer obviously is thinking in terms of binary. Okay. So we talked about in binary, first position is 1. The second position is 1 times 2. The third position is 2 times 2. And then the fourth position is 4 times 2. So you can see that is essentially 2 to the 4th power. So you get, this is considered 0. So 2
is
what's that?
Exponential, is it right? The exponent number, the exponential numbers?
Exponential. So this one is considered 2 to the 0 power. This one is considered 2 to the 1st power, 2 to the 2nd power, and then 2 to the 4th power. And you go out and out and out until you get to, let's see, you get 5, 6, 7, 8. What's that? Say it again.
It's 256 until 255 is I think like 1 byte.
Right, it's 256. So because we start at 0, you can have a possible character, you can possible of 256 characters, but what that means is your max character is 255 because we have to include that 0. I see a note because I see that 7, you're confused because that 7 equals 1111 and 15 equals 1111. That's right. That's exactly right. And between this 1111, because we're moving into that 4th position, we have to add a 1 to the beginning of that and flip all the following numbers to 0 and start again at 0, 1, 1, 0, 1, 1. So essentially this pattern restarts. All right, so this in the decimal numbering system is 999. But if you run out to the internet and you Google what is the decimal value of 999, you're going to get a much different answer. Go ahead and use your browser, go out and just do a Google search real quick. What is 999 in decimal? All right, and I see somebody put it in the chat. It is, I'm not even going to try to pronounce that number, but it is a lot of 1s and 2 zeros. All right, and this is just taking the concept in terms of decimal numbering a little further. So this is 10 to the 0 power is the 1's place, 10 to the 1 power is the 10's place, 10 to the 2 power is the 100's place, 10 to the 3 power is thousands. And this is a little statement that unless you have studied decimal numbering, you probably aren't going to get it. But essentially, there are only 10 types of people in the world, those who understand binary and those who don't. And essentially, it is because the figure for 2 is actually in binary 10. And so it's that common phrase. There are only 2 types of people in the world. And now you can go tell other people that joke. This is another method to kind of see how computers interpret binary. Computers, again, they only understand, go back to 0. So computers only understand that 1 or 0 signal. And that signal, excuse me, that signal is actually interpreted by the computer through transistors. And we talked about transistors yesterday or Monday. And essentially it's those teeny tiny little devices that can interpret electrical signals. So your electrical signal, much like a light switch, is just going to be on or off. And so the transistor can actually interpret whether electricity is running through it or not running through it. And so when the transistor says, all right, there's no current, it actually reads that as a 0. But once the transistor reads that there is current, it records that value as a 1. And so that's why transistors are so important to the makeup of our CPU, the makeup of our computer. So to see that represented in light bulbs, where we go out to the 128th place, you see there's 8 positions here. If we want to send the computer a 0, essentially we don't send any electricity, it reads that as nothing. If we send them electricity, it actually, in our decimal interpretation, it reads that as a 1. If we want to send them the signal for 3, then we actually send them this particular code, where we've sent them a value of yes on in that
I think when you make a game mode off on and choose the numbers, you can, yeah.
Okay.
And then like choose like one of one, like 64 or 32. One of
That's
them.
easier because I was scrolling through. Thank you for that. We had that question earlier of what is 999 in our presentation. And in truth, decimal only understands up to 255 characters. So the combination of characters that we can actually give, at least this simplified version here, is 0 through, let's see, 0. Oh, it's only letting us do 1.
You should choose one of these numbers that we have here on the lamp, like 64, and you can play with the numbers, and that works. Like 64 or 32, whatever you want, you know. And yeah, then go up. No, for that with numbers. Yeah. No. When you click on that arrows, you know, that's right, and click on the arrows. That up number. 1, 2 until 8, and then on bulbs. When that's too much. It's 8. What's gonna be 2, 7? Yeah, 7 will be enough for that one. 7. Yeah, and then click on the bulbs. That works on the bulbs, but the other one, bulbs. The bulbs one on.
Okay, gotcha. All right,
Yeah.
I see how it works. Thank you. I was just going through the numbers to kind of represent the values of, you know, positive signal versus negative signal, but this is kind of cool. So let's see. If I want to see the number 1111 represented in the game, we actually saw in our spreadsheet that 1111 is 7. So if I go here and I put in 7, sorry, I'm having trouble typing. Now, in order to represent 7 in terms of our light bulbs, I actually have to send a signal to the computer in the 1's place, 2's place, and 4th place. And it actually tells me I'm right. Similarly, we had 15. And we know that in our spreadsheet, 15 was actually 4 1s. Now, if the system interprets a positive charge in those 4 positions, it knows that we're actually sending the signal, at least in the decimal conversion, of the value 15. All right, you guys can see that again. And this is similar to that game, and it essentially is building out all of those places that we saw, so that 2 to the nth power, 2 to 0, 2 to 2, 3, 4, 5, 6, 7, 8. In computers, they consider the decimal numbering system up to 8 characters. And they came to this decision through trial and error. And so that's why when you see decimal numbers, you see them represented in 8-character representation. So on our spreadsheet, when you see the decimal number for 15, the way you'll actually see that written out is they provide all values for all 8 spaces. So you'll get 0, 0, 1, 1, 1, 1. Go ahead and feel free to kind of play around with this particular chart. We're not going to do it right now in class, but revisit this if you want to experiment with decimals. I'm not going to cover it right now, though. All right. So feel free, if you would like, to go back to that website. I'm going to put this in. Oh, thanks, Benjamin. You actually put it in there already. I see that. So go back to this and start playing around with the numbers and see if you can get the right combination of lights to the different the numbers on this particular slide. So we'll start out with the first one. So go ahead and Pear Deck, take your mouse and feel free to use the light bulbs to kind of help you figure it out. But in the binary number system, what number is represented by, is the representation of 14? Go ahead and just put your little responses on that number. And go back to the options in case you don't see those. All right, so the actual value for 14 is A. And we can see that in our spreadsheet. We have 1110 is 14. Now, if you try to write out this chart of binaries 1 through 15, if you've tried to do that, this will probably speed up a little more, but I want you to take the other options on this and try to figure out what the actual numeric representation for that number is. So we know A is 14. What is 1010? What is 1000, 1111, and 1001? So take a second right now. I'm going to give you a few minutes to kind of explore how the decimal numbering system. Henry is on it. And then once you think you've got the number in mind, go back to this little light bulb test. Put in the number you think it is, the decimal number you think it is. Let's see, I've got for the first one, or B rather, I'm seeing that people are getting 10. So if I go to B, I see that it's a 1011. That means I've got an on charge in the 4th position, or actually the 8th position. And I've got a on charge in the 2nd position. And that actually is right. That's the right representation.
also, when you click on the bulbs again, it shows the numbers as well on the when you turn off. No, the bulb one. Yeah. Sorry. The bulb one, the bulbs. You just turn off and it shows the numbers also.
It's on the left.
Okay.
Left side.
The left side, yeah.
That shows the number when you play, and then
Okay. I see. Okay, number C, or letter C. Letter C is actually just a little different from B. In that instance, from B, we're just having to flip the flag in the second position, or flip the number in the second position down. So where we had 10 in our previous one, what do we get if we switch that flag in the second position to a 0? What number does that give us? And we can see that we get, for 1, 0, 0, 0, 0, we get 8. Because in between 1, 0, 1, 0, we actually have the value 1, 0, 0, 1. Because in 8, we had 0 in the first position. The next number, we had to flip that to the 1. The following in the sequence, the next one in the sequence, we had to move out a position, which reset our first position back to 0. And that's where we got 1, 0, 1, 1. And so you can see that for D, we get 15, and for E, we get 9. So if you got all that, great job. Okay, so this one is not. Oops. This next one is not on the spreadsheet. So go ahead and take a stab at it. Which number is 50? All right, let's see. What's everybody picking?
one is the first one.
They're picking the first one. 1, 1, 0, 0, 1, 0. In a little different way to represent, and the first one is right, by the way, a little different way to think about the decimal numbering system is where we have our places. So let me find a slide with our different positions identified. Okay. So where we have our positions identified, and this is our first position, second, fourth, eighth, etc. When we use numbers in the first position, and we have a possible of 2 combinations that we can use. So basically, it's listed out in the spreadsheet that you see for the first position. Those are your options. And then when you get to the second position, you have a possibility of 2 numbers at that point as well. But when you bump out to the fourth position, you actually have a possible combination of numbers 4 different ways. And then when you bump out to the 8th position, you have the option or possibility of using 8 different numbers. So that's why when we go back to looking at something like this, you can see that you have a possibility of 8 numbers at this position, and then it jumps depending on the number of actually numbers that you're using in your string. If you have numbers in up to 6 positions, you have up to 32 different possible numbers that you could pick from. And then ultimately all the way up to, if you're providing digits in all 8 places, that is a total number of 128 different possibilities. Add them all up, that is where you get that limit of 256 possibilities. All right, go back to the internet. I want you to do another search for me. What is 11010? Thanks, Benjamin. All right, so let me see what you're saying. That's right. I'm seeing a lot of dots under 26, and that is correct. All right, we're at break time, and we're going to leave the topic of decimals. Hopefully you kind of get the idea that it's a combination of ones and zeros. It is what the foundation of logic is based on. It's a true or false way of interpreting signals. So go ahead and take a break. We'll come back at 8 p.m. Eastern. Make sure you stretch, maybe get something to drink, and I'll see you back here. We didn't talk about calculating binary manually, but I did want to point out that it is possible if you're provided the decimal number and you need to figure out how to represent that in given the binary number and you need to figure out what that is in decimal, since we're working with a factor of 2, you can actually do division. And the areas where you actually can divide evenly, we'll say, you represent that in your kind of your final binary number as a 0, we'll say. Let's do this. All right, let me show you instead. I'm trying to explain it is a little weird. All right, so when you have a number 12, you can actually divide 12 by 2 and you get 6. You do not have a remainder, right? So there's nothing left over there. Then when you go and you try to divide 6 by 2, you get 3. And you don't have a remainder there. That should not be that. Let's see. All right. Now, because we have 3, we go through and we divide 3 by 2. He's doing that. And when we try to divide 3 by 2, 2 actually goes into 3 one time, but then we have 1 as a remainder. And then finally, we have to divide 1 by 2. And if you divide, hang on. All right. Then if you divide 1 by 2, it actually doesn't go in there at all. And you have 1 as your remainder. So when you finally look at your results, you actually write this out as your binary version of this is going to be 1100. So you take out of all your remainders and you list them out from last to first. And that's because when you divide by 2, it's pretty easy. You're either not going to have a remainder, it's even, or you're going to have a remainder, it's odd. All right. I don't know if that was a little easier way to, oh, somebody wants me to make it bigger. There you go. Is that better?
It's much more. Thank you.
All right. As promised, binary numbers, moving away from them a little bit. Obviously, everything is based on this binary system. I talked about true and false. A lot of times when you're working in databases and form, object-oriented programming, where you're storing data in databases, wherever you see the storage of values like yes and no, yes is going to be the value 1, no is going to be the value 0. So you kind of see this concept of, for those out of values you only have 2, you kind of see that represented when you see forms on the internet or going through applications and you have a checkbox. When the box is checked, it's a 1. When the box is unchecked, what's actually being stored in the database is a 0. So again, as you go through and you start programming, especially programming things to be stored in kind of a relational type database, you see that at least. All right, back to our slides. So when we think about number representation, you often see numbers represented as integers, but numbers can be stored as a text value. Of course, when you think of numbers, you think of 1, 2, whatever. But when you try to write out, say, the decimal number, you have all these leading zeros that you don't normally see leading zeros when you're just thinking of numbers. So in the number world, when we're trying to store numbers, we can store numbers as a string. So we can say, all right, this number, even though it might be the number 3, I want you to show me that number in with 8 digits, right? So you would have like a 000000003 written out, so a string of digits. You can also see numbers represented as integers, so whole numbers, right? 1, 2, 3. What you're not going to see is you're not going to see decimals with integers. There's no partial value. And then you see floats, and floats is where we do record numbers in decimal format. So 12.25, $5.23, that sort of thing. When we talk about storing letters, and we keep that the computer is expecting binary format, we have to come up with some way of providing the computer a numeric value, obviously, because we just went through the whole exercise that for each binary number, it represents a number. But then when we try to send signals that are actually letters, this is where things get a little tricky. And when computers first came out, everybody was kind of doing their own thing, especially, you had a couple different companies trying to, come up with a way to, at the very, very early stages, how to interact with a computing system, right? We didn't have PCs and things like that. We had these huge machines that we would enter in like punch cards, right? We would say, all right, machine, read this punch card. And if the card had a hole punched in it in one position, the computer interpreted that as a 1. And if it didn't have a hole in it, it interpreted the value as 0. But then when we started getting a little more advanced with computers and using keyboards, we had to come up with a way to instruct the computer basically what we were telling it through the keyboard. So we no longer had these punch cards, which were basically 1 or 0. We had what you use today, probably use a QWERTY keyboard. You may use something else. But what you see on the screen here represented is these are the commands that come from a standard keyboard. And you'll notice there's no special characters, right? You don't see like is it oolong? You don't see any of these like, Y with a little tick above it, that sort of thing. This particular table represents how developers in America standardize values taken from the keyboard. And so it's known as ASCII. So if you ever are using a computer and you see something that says, this is ASCII, it's the standard. And it's a standard originally put together on the American side of computer development. And that's why ASCII stands for American Standard Code for Information Interchange. Now, it's great, yay, but the rest of the world was probably using their own standards. So when computers started to become, linked together, say through network and then ultimately through the internet, we had to have a better universal interpretation of standard code, and we'll get to that. But in the beginning, there was ASCII. And a lot of people adopted ASCII all over the world, but it was the first time they were like, oh, we got to standardize this, right? So you can see on the screen here, this chart, it's a little bit of an eye chart, but at the value of 0, you can see that values 0 through 64, we don't even get to letters in our little conversion chart here until number 65. So when we're talking about decimal, if we're sending decimal values, I type in Control A, and that is actually the binary value 1. The computer is interpreting that as, what do we say, 0000 0001, right? And so for every decimal number that we converted binary to, it actually also represents these commands out of the keyboard rather. ASCII only can be represented with 7 bits. So we talked about that our binary numbers, they had 8 positions. When we start storing the binary interpretation of for ASCII interpretation, we only use 7 out of those 8 positions, which means we only have up to 128 combinations of letters and symbols. And you can see, so it's a little hard to see. Let me see if I can show you. This is a table of the ASCII conversions. And so you see we have 128 possible options, but because, again, we have to include for 0, the conversion to decimal only goes up to 127. Okay, so let's take a look at how ASCII interprets or converts our signals in binary to actual numbers, letters, symbols. I'm going to go back to my little spreadsheet here with our conversion table. I'm going to make it a little bigger. So the way ASCII kind of interprets our signals is when we transmit a binary value equal to 72. And we talked about how binary is represented, binary represents the number 72 through all those 0, 1 combinations. So when we want to send, or when we want to see a ASCII value, we actually are, the computer understands that as, okay, you're sending me the binary for 72. And I understand that 72 in a decimal format is actually, I go over to my little chart. This is my decimal column here. I see that 72 in character format is actually H. So if we come back to our little screen here, we know that the character that should be returned here, where we have a decimal number 72, we should see an H there. Similarly, when the computer needs to understand what letter it should represent on the screen for 73, we go to our table, we've got our decimal numbers, find 73, and we see that 73 is I. Now, it is, obviously they took numbers and they, in the order that the alphabet runs through from A to Z, you're going to see a sequential numbering. And then when you get to Z, you have a couple of numbers that aren't letters, and then it starts lowercase, and then sequential numbering. The system, the system interprets the command for capital letters differently, or interprets the value of capital letters differently than the value of lowercase letters. And that is significant because we do, in many cases, need to transmit case sensitivity. Obviously, if we're writing out a sentence, we don't want to see everything in all caps. We don't want to see everything in lowercase. And how do we delineate between the two? We're actually sending 2 different values. So 65 if we want to see an uppercase A, 97 if we want to see a lowercase a. All right, so back to 73. That is I. And so in the second position on our screen, that's an HI. And then the final value that we need to find the ASCII character for is 33. I go back to, I finally got that by, if we go back to 33 here, it's a exclamation point. So put it all together. All right. So that was the American standardization very early on, and it's stuck. You still see ASCII represented today. If you ever have worked in HTML, you often see conversions for letters in HTML referencing ASCII values. One thing that is on this particular chart here, you can see that the HTML interpretation for the character ampersand is actually ampersand #38 semicolon. Well, that is that 38 is also what we see in the decimal. So there are some parallels there. And, that's older HTML, very, very basic HTML. Okay, so now we get into this new standardization, and this standardization is known as Unicode. And you will see Unicode referenced a lot of times in software. It is also known as UTF-8 or the Universal Alphabet. And it's essentially an ordered set of over 1 million characters. So now we're not limited to 128 characters. We have all of our special characters, even the ever popular emoticon. And Unicode, it's not software. It's actually a standard, right? It is a 16-bit encoding standard. And when we think of 16 bits, we're thinking in terms of a possible string of 16 places. And so you can see that in Unicode, it looks a little different. First, you see that the representation, you'll see it as a U plus and then a combination of numbers, or a combination of numbers and letters. So they've kind of introduced something out there now greater than just 1 or 0. We have, depending on how large the value, again, there's certain numbers of bytes that will be used. And you can see it's reading now in a left to right, whereas when we were working in binary, we're kind of reading it from right to left. So let's take a look at the differences between ASCII and Unicode. So ASCII is character encoding for electronic communication. And when you think about Unicode, this is a computing industry standard, right? So where ASCII was kind of that American early stab at it, this now has taken into consideration, all different types of characters used all over the world. Really, we were in desperate need of something like this. Again, ASCII only supports 128 characters, and Unicode, many. ASCII, we only had 7 bits, 7 positions that we could use to represent those 128 characters. Unicode, we can actually have an 8-bit Unicode system, a 16-bit Unicode system, and up to a 32-bit system. Now, the benefit of ASCII, because we're using less bytes, less data, it doesn't take as much space up. But obviously, the cons are outweighed by the pros in terms of Unicode, even though it does take up more space. And obviously, when we think of space, we think of efficiency, we think of speed, and that's how, when we talk about requires more space, if we're using up more space, there's more of a tendency that we reduce speed, we reduce efficiency in terms of storing information, that sort of thing, and retrieving information. Okay, Unicode. Up there I have 3 different emoticons, and you can see underneath the emoticons, that's actually the Unicode for that particular emoticon. So when you find a cat with hard eyes on your keyboard, the code that you're actually sending the computer, what the computer understands that to be, is actually this U+1F63F. So I do not have a quick little mathematic method to find the Unicode for something, but you know, like we had for binary. Let's talk about voice. How do we store voice? How does that even happen, right? We've talked about values that you can enter onto the screen digitally, right? You can enter numbers, you can enter letters, but when we get into voice, audio rather, that's analog. And what we need to do in order for that analog to be understood in a digital environment, we need to have some sort of conversion. So to understand that conversion, you have to understand how audio waves are recorded, right? And is what we have when we hear audio or when we're trying to record audio is it's represented in waves, right? We have different amplitudes to sound. So when we're recording audio, we're actually recording those various amplitudes at a specific point in time. So I've essentially, if you look at the graphic on the screen, I've essentially made some noise at a low amplitude at a specific second, we'll say, followed by increasing amplitude in the seconds following. When we've recorded our audio in wave format, what the computer does is it actually has a device. It's an audio to digital converter that knows that depending on the amplitude that you send over, I can actually assign a binary number to that value. And of course, we graph out sound waves on a graph where your X and your Y values can be recorded as numbers. And that's how we derive that digital value or that binary value. Now, at this point, the audio is digital in the computer, but we're only recording audio. We still haven't figured out how to hear it again. So I talk into the computer using the microphone. In our technology, we want somebody else to be able to hear it. So that introduces another component on the computer, which is the digital to analog converter, DAC. So it takes our binary values, converts them to back to waves, right? And then that is how we receive sound out of our speakers. And if you're talking somebody to straight using a microphone and speakers right there, that's easy. That's an easy conversion. But where this actually gets, kind of, I guess we'll say it kind of added flexibility to recording sound and distributing sound when you took that analog value and you stored it on some device to listen to later, right? So in real time, you're talking into a microphone and you've got a speaker next to you. They had that kind of microphone speaker set up at weddings and conventions. But when we started introducing the computer, we added flexibility to recordings where we could record, digitize, and then reproduce in other formats down the road. We also came to a point where we could improve the quality of audio coming into the computer. And let's take a look at the next slide. All right. So a little more intricate information about how that analog that analog value, the signal, is actually interpreted by the analog to digital converter. Is essentially you get your analog signal, goes through that ADC, and then the ADC actually can assign binary values based on the, we talked about it, amplitude. All right. So depending on the amplitude, they have a graph laid out. You can see these are our scales across the bottom, and then these are the binary values that we're assigning to the amplitude. And so if you get a sound wave that is high in amplitude, it'll be assigned a binary value of, say, 1111. Obviously, low amplitude, you're going to go back down to the the binary for nothing, which is 0. But the thing to keep in mind, again, is that time scale. And so the better you can record audio, so the better the frequency that you can record audio, the better the quality of the digitized output is going to be. Because when we go along the signal, if I am recording at a frequency rate of every 1 second, there's actually differences in when I'm speaking in the intonation or the amplitude of my voice. So if I reduce that recording frequency down to a half a second, so it's recording the sounds coming out in a half a second, then it's going to get more detail about how that voice is changing or how the audio is changing. So whenever we talk about, audio recording, frequency, the term frequency comes into play, because the greater the frequency, so the more often you can pick up that sample of audio, the more you can accurately kind of reproduce that same value. But in between those increments of sampling, you just lose that audio. And so that's why sometimes when you hear recordings, older recordings especially, it didn't really sound like a real person, thready, or it just doesn't sound like a person. There's a little strangeness to it. Likewise, digitization. When you hear somebody and they sound digitized, that's a poor sampling of audio as well. The graphic is actually showing like a 3-bit representation of a converter. But the more complex your converters get, again, the more nuance you're going to be able to record. And I use the term sampling or sampling rates, sampling. The other way you can hear that same thing mentioned is you may hear bit rate, the term bit rate used, or quantization level. So there's a couple other terms that you can use involved with audio. So your bit rate, your sampling rate, that sort of thing. How about image and video representation? Image and video representation, we actually use a combination of 3 colors, and those 3 colors at different magnitudes. So you can see the colors on the screen here. We use RGB when we're talking about visual or display. If you ever go shop for a monitor, it says it's an RGB. monitor, right? And these three colors are really the main colors that the eye takes in. They're also referred to as the additive primary colors. When you combine the colors together, you can get other colors. In the digital world, each color has a number assigned to, we'll say, its shade, right? So shades of red have a number 0 to 255 assigned depending on its intensity. Same thing, green. Green, you can have a green at 0 intensity. You can have a green at 255 intensity, and same thing for blue. So we talked about decimal. Decimal also, it is represents up to 255 values. So really each color can be represented as an 8-bit number. And that's very convenient because we just happen to do everything in the computer using an 8-bit number when we're working with decimal. And you can see on the left here where we've assigned red 72, green 73, and blue 33. It actually, when they're combined together, they generate this color to the right. All right, I'm going to click this and bring up a website. I'm going to put the website in the chat because I want you guys to see. Oh, thanks, Benjamin. I appreciate that. All right, Benjamin is on it. So let me bring that over here. Start off with an example in our little RGB calculator of a bright red color. And essentially, when we're talking about the intensity of red, obviously 0 being the least intense and most intense or purest red, 255, you can see if I say everything is 0, 0, 0, that really is an absence of color, right? I'm requesting an absence of color. And we know from the, basic learning about colors is, black is the absence of color. So when I go in here and I change the value for red and say not 255, which we saw, but maybe I say 65, you can see that puts me up on that 0 to 255 scale right about here. And that's a lovely, say, maroon or brick color, depending on how your monitor is configured. Similarly, I do that same thing with, I do that same number change with blue, or green rather. At 255, that is a really bright, pure green. Let's take a look at 70 green. Let's try to make that work this time. All right, and then 70 green, that is a more muted, rich kind of forest green. And of course, do what you would love to do with blue. Go ahead and play around with the blue color numbers and see what you get. I'm going to try to get something that's like a navy. That's kind of navy, 65. All right, that's pretty simple, right? But in our example that we saw on the last slide, we can do values above 0 in all three, with all three colors. And so once you start introducing different numbers in the scale for each color, that then takes you away from just these colors that are on this red spectrum or blue or green. And now you're combining things to get something totally different. Let's see, I'm going to increase my red values to 60. Let's see what we do. That makes the green kind of from a forest green to a military green. When I make the blue value 200, because I've got some red and some green in there, it's not that bright green, but it's still pretty bright. It's still a strong blue rather. And then if I keep red low and I make green and blue high values, I get a turquoise value. So this really is just to show you how the computer is interpreting those binary values that are converted to decimal values that the computer then can work with to generate color. Now, we've talked about how we generate color. How do we actually get that color to become a graphic? And you can see that on the screen, I see something that looks like a grid. And the grid is actually a combination, a grid of what we call pixels. So I don't know if you've ever taken, I did this a lot when I was a kid. I'd get really close to the screen and I'd look at all the different pixels on the TV. Pixels back then were a lot bigger, and you can still kind of get close to your screen and kind of see the different pixel colors, which is that red, green, blue. But pixels are so fine now. Obviously, the more pixels you can fit into the rectangle that is your screen, the higher the quality of what you're trying to represent becomes. It's similar to that sampling of sound. The more frequent you can sample sound, the more accurate the value. The smaller you can make those adjustments to pixels, ergo the adjustment to colors on your screen, the clearer picture you get. And so that's why in image video technology, you see resolution referred to. And so the greater number of pixels per, they'll measure it per square inch, the higher the resolution, they call that. So if you've ever shopped for a monitor or a laptop, that becomes part of the vernacular that the sales folks or that company that created that laptop, that it becomes part of how they're trying to sell that to you. Obviously, with greater resolution comes a higher price tag, because you are actually having to add more components to make that device. This is a image and pretty basic resolution, right? Not too many squares. What they do in computing is for each pixel, they assign a color. So say for this red color, you saw the previous exercise that we went through when we added those 3 different color values. So this particular pixel can be assigned one combination of those color values. So this little guy here is some red, some green, some blue, always. This one, white, it's some value of red, of green, of blue, right? So you're always getting those 3 numbers combined, which the computer can then interpret to be a color. Anybody tell me what the color values would be for the white pixel? I see some typing. Yeah. Whereas black is the absence of color. So we saw that was 0, 0, 0 in all 3 of the colors. If we max that out at 255 for everything, that is all colors. And that's what we learn in school in like kindergarten is black is no colors, white is all colors. So we assign the different color combination values. Each pixel can only get one color. And then we move into, if it's a moving image, where we start to see different pixels brighten, darken, change in color, depending on what we're trying to display in the image. This is just another representation of what I was talking about in terms of resolution, or in this case, definition, right? If you shop for a TV, you've got your standard definition. And if you are, got a lot of money in your pocket, you're going to walk in, you're going to say, I want a high definition TV. So you can see standard definition. They refer to that as a 704 by 576 pixels. So when you look up close at the screen, you're going to see 704 pixels across, 576 pixels from top to bottom, totaling the screen as, thanks, Benjamin, we'll break in 2 minutes, 405,504 total pixels. Then when you get into high definition, now your number of pixels across and down increases quite a bit, like, 15,000. Not 15,000, 1,500,000. So when we start talking about the latest technology, ultra high definition, see, they've packed in so many more pixels across and down, and now we have over 8 million pixels in total on the screen. So that's a lot of pixels, makes for a very enjoyable viewing session, nice movie. And now, of course, we talked about recording audio. They have, different ways of sampling audio even better today, so that the audio and the video combined make for some very accurate reproductions of real life sound and display. Okay, so 8:44. I'm going to break here. All right, we left off. We're kind of giving our feedback on how the class was going. A lot of confusing topics, a lot of resources out there to explain it a little differently, maybe more moving pictures, things like that. Obviously, if one explanation doesn't resonate, perhaps somebody else's explanation will. I find that in my own learning, that can listen to someone explain something, and just maybe the order that they explain things or the words they use don't 100% get, but then I may see it represented graphically or explained another way, and it's like, oh, okay, I get that concept. So don't forget about going and searching on the internet for other resources, and definitely don't forget about reaching out to me and letting me know how I can help. We return back to our topic. Now we're going to talk about bits and bytes. So we've been talking about sending signals, right? This binary number, and we're sending signals. So essentially, when I talk about sending signals, that's where we're sending that machine code to and from, whether it's the operating system is saying, okay, this particular value is binary for on, this value is binary for off. It's using those values to interact with hardware. It's using those values when you are running software. And so all of that, we talked about how we had that temporary storage, we had the RAM. So that is one application of using the binary numbering system, send signals back and forth between things. But then we also talk about at the elemental level of long-term storage, right? Also, everything's being stored long-term in our drives that we talked about on Monday's class. So we're transmitting signals through interactive working with the computer, but then also we're taking that binary data and we are recording it to potentially access another day. So bits and bytes. When we talked about the binary code, we saw that we had 8 positions, right? And so each one of those positions is considered a bit. Combined, that entire code of 8 bits is considered a byte. Where we have our transistors within our CPU, we actually have talked about the fact that those transistors can interpret values of 0 or 1. And I've talked about how that is also used when we're recording values with a true or false kind of frame of reference, or a yes or no frame of reference. Right. These guys, they're kind of showing us again that light bulb exercise that we did, just indicating that, you know, for every on light that can be interpreted to us, you know, from a binary lens, that is a 00110010 code, right? If we're trying to convert that to decimal. The entire combination of 8 bits or 1 byte represents 1 character, right? We also talked about the fact that if the computer were required to interpret signals greater than just 2 values, 0, 1, that would be a heavier load on the processor and how the computer can actually decode what we're sending it. So essentially with that binary, the computer only has to interpret 2 states. All right. When we talk about bits, bytes, and we're talking about storage, the greater the storage capability, the more bytes it has, right? So if bits are our individual building blocks and bytes are our entire binary code, then when we're storing bytes on a hard drive, and a byte is a single character, in order for us to store an entire word or an entire character, an entire sentence, then we start increasing the number of bytes that we need to store data. So the letter A is 1 byte of storage, but the word the is 3 bytes of storage. And so those are just small pieces of a sentence. And if you talk a lot or type a lot, you're going to use up a lot of space. The further out you go in terms of size, the terminology that you use to label how much space you're using up, it mirrors kind of the prefix terminology we use in the decimal numbering system. So, you know, we have, say your, you know, a meter, a kilometer, that sort of thing. But in the bits and bytes world, where we have 1 byte, once we get to 1,000 bytes, we actually refer to that as a kilobyte. And obviously, if 1 byte is 8 bits, 1,000 bytes is 8,000 bits. In actuality, when we store data, we are storing 8 bits. So we don't store partial bytes, right? When we store something, we are storing all 8 of those positions of zeros and ones. So when we talk about a kilobyte, it really has to be a factor of 2. And because 1,000 is not a multiple of 2 per se, or 8 rather, pardon me, because 1,000 is not a multiple of 8, and we have all 8 bits that we've got to store, that's where you start seeing values when you're looking at shopping for hard drives and things like that. Even, you know, screen resolution, you are seeing values represented by a factor of 8. So the closest thing to 1,000 kilobytes that is a factor of 8 is actually 1,024. So you will see 1024, 2048, these values to represent different things. Now, Benjamin put a graphic in Slack that represents how the progression of terminology builds as your the size that you're storing, the size of data that you're storing gets larger and larger. So 1,000 bytes is a kilobyte, and then 1,000 kilobytes is a megabyte. 1,000 megabytes is considered a gigabyte. And then if you've bought an external hard drive lately, you are probably looking at things that are measured in terabytes, right? So 1,000 gigabytes. And usually when you shop for things in the terabyte size, they are not very large, right? I think a lot of the commercial sizes are in the single digits, like, you know, 3 terabytes or, you know, something like that. That's because the more size, the more space you have to buy, the more expensive it is. And the same is true for when you start working with servers. The more space you have to purchase, you get pricey. And when you think about all the space a company has to have to store a database system or store a web page, it can get pretty astronomical. We talked about the exponents, the factor of 2, and represented it by, exponentially. A kilobyte is actually 2 to the 10th power, which is also 1,024 bytes, or what we refer to in the biz as 1024. If you look at how files are stored on your hard drive, I'm going to show you one of mine. You can see that this is a single file in a drive that I have on my hard drive. And when you look at a file in your file viewing app, in this case, it's Explorer on Windows, you will be able to see the size component. If you don't have a view that's a detailed view like this, you can often right-click and look at the properties of a file, and it'll show you the size. It's kind of that metadata that we talked about on Monday. So Word files, you can see the size that they are. The less characters you store in your Word file, the smaller that file is going to be. And that also plays into why sometimes when you're on a website and you come across a field and like, explain to us why you want to work here. And they're like, limit your response to 4,000 characters. That's why they just haven't set aside enough space for you to truly tell them how you feel. All right, so we talked about a kilobyte. A megabyte is 1,000 kilobytes. So in a sense, if a kilobyte is to the 10th power, a megabyte is to the 10th power kilobytes. MP3s, music files, video files, they're all stored in terms of bytes as well. Gigabyte, just a different way of representing what Benjamin put in Slack. A gigabyte is 2 to the 10th power megabytes. So if you're counting all the way back from bytes, a gigabyte is 2 to the 30th power bytes. And then a very common method of storing data and storing our bytes is the thumb drive, storage device, flash drive. And then terabyte, of course, again, 2 to the 10th power of gigabytes, 2 to the 40th power bytes. And this is one of those external hard drives that I was talking about. And this is where you really can purchase a lot of space, like a terabyte or more. For some reference, I guess, to take these bits, bytes, terabytes, and put them in a little different perspective. If you think of size in physical terms, a bit is, say, like a marble-sized dash of water. So a marble full of water. A byte, think of that as 1/8 of a cup. And a kilobyte, 9 gallons of water. And see, it's just, again, using the word exponential, it just increases exponentially. So kilobyte, 9 gallons of water, 1 megabyte, an above ground swimming pool. So something you may fill a bathtub with to an entire swimming pool. And then 1 gigabyte is a football field sized pool of water, at least 3 feet deep. And then if you are trying to visualize a terabyte, it's a football field sized pool of water, half a mile deep. So that is huge, huge and huge and huge. All right. So go ahead and draw on this pyramid that I have on the screen here. If you look on the pyramid at the bottom, it says 1024 bytes. Draw on there where you think each one of those terms we just discussed are, or fall. So this being even the bottom of the pyramid, we'll say that is the largest amount of space, right? The greatest amount of space, that's our entire football field of water, a half a mile deep. Go ahead and write on there what term would that be in bytes. And then our smallest value here. So what do we call 1024 bytes at the smallest level? Is it letting you draw on the screen? I don't see the results in the Pear Deck. They kind of did it different. If this is you guys able to type that in? If we're looking at the representation for up here at the top, so we're just looking for a representation of 1024 bytes. That's actually going to be our kilobyte. But as we increment in size, we go to gigabyte, terabyte. So that's how we increment in size. And I kind of tried to visually represent the smallest storage size at the top. So that is our smallest little wedge of the pyramid. And then, so we're thinking about our gallons of water versus football fields of water. But that pyramid could be interpreted a couple different ways. That's just what I was looking for. So I see some good responses on the screen. Yes. So smallest storage above bytes is our kilobyte, megabyte, gigabyte, terabyte. So that's the order and size of our storage. Okay, I'm gonna open up Kahoot now. So this is your chance to show us what's stuck, right? Also show you where maybe a concept didn't, sometimes I drift off when I'm trying to learn something. All right, so this is where you're going to go. You're going to go to kahoot.it, and the game pin you are going to use is 3125642. I'm going to go ahead and paste that into the Slack chat. I see you guys coming in. Okay. Got a lot of folks, so I am going to get started. Feel free to pop in. Computer Fundamentals 3, Kahoot, Data and Storage. If you're new to this, again, it's going to show you the question. It's going to give you a certain amount of time to answer. So on your screen, you're just going to click the one you think is the answer. At the end of time, it will allow us to see what the answers are, and then can have a little mini discussion on why some of the other answers may not have been a good answer. All right, how many bits are in a byte? 8. Yeah, so bits, the smallest building block of storage, it is just 1 or 0. A byte is going to be your 8 kind of character code, which is representative of a character that you would use to interact with the computer, like A or control F, something like that. So bytes represent a single character. All right, let's see where we land. All right, Mustafa, starting us off good. All right, let's do next question. What does ASCII do? This is what I thought was tricky, because ASCII actually is it represents different characters you might find on that QWERTY keyboard, but it's not only numbers, it's not only characters, it's also like control S and things like that. So it was a little tough to kind of interpret what they were asking for, but yes, the best choice would be it represents text in computers, but it can be a letter, it can be a number, it can be a character like an apostrophe. All right, let's see. Steven? Thomas is the highest climber. Way to go, Thomas. How many bytes are in a kilobyte? Go back to Benjamin's cheat sheet. All right, 1024. That is how many bytes are in a kilobyte. All right, excellent. Let's see. We've got F1309 VC, highest climber. They're coming for you. What is a gigabyte? All right, this is 1,000 megabytes. So a gigabyte is 1,000 megabytes. All right, have some movement there. Sue, 4 correct answers in a row. Way to go. How many bits in 2 bytes? How many bits of a sandwich can you eat with 2 bytes? 16, that's right. A byte is 8 bits. 2 of those, 16. Oh, you're back, Mustafa. How many bytes are in a kilobyte? Really, when we're talking about bytes in reference to megabytes or kilobytes or terabytes, your multiplier is 1024. So 1024, 1024, 1024. They tried to fool us with 1042. All right, that's a moving. What does ASCII stand for? All right, the American Standard Code for Information Interchange. Next question. A megabyte consists of, this is tough. This is a tough one. It's where expressing the number exponentially in some cases. All right, 2 to the 20th power bytes. I couldn't tell you that off the top of my head. I gotta go back to my notes. All right, Sophia. One terabyte equals. Yep, 1024 gigabytes. All right, let's see what happened there. Allison? V. Sophia. All right. Nicely done, guys. Runners up. Q quite C. So if you are F1554, good job. And then it hid the other one. So if you were a run up, great job. Great, everybody. Thanks for trying to all right, great. Can't read it. Is that Hannah? Am I reading it right? Nice job, guys. Okay. So let's get back to our class. So that's a good recap of kind of the storage and measuring storage. I want to go back to, we shopped for a computer on Monday, right? And I want to go back and take a look at that again. So here are the 3 different Macs that we were looking at the other night. And now that we've kind of gone through the hardware, the software, and now storage, let's take a look at how that stacks up with our 3 different versions. So we talked about, first things first, at the top of the screen, we talked about storing visual video. So we talked about pixels, resolution, and you can see right off the bat, they've got the 3 different sizes. And when you dig deeper into those 3 different sizes, you also want to consider the resolution. Let me see if they give us the resolution. Yeah, they were just telling us that they had a retinal display. We don't get the resolution, which is what I was hoping to see. All right, great sales pitch. All right. So the other night on Monday, we talked about our processors, our CPUs, our cores, and we learned about that our CPU can have multiple cores. We talked about RAM, and that's that temporary memory space. And that was here. You can see that the temporary storage on these differs between models. And then that permanent storage, that hard drive space. So this one, 2 terabytes, this one, 8 terabytes. And so that kind of leads into what we just covered, which is how many bytes does this machine allow you to store on deck? This doesn't tell us much about resolution, but it does size. Let's see, anything else. So going back to our computers, that's kind of some of the things you want to look out for. I think maybe PCs will give a little more detail. Let's just look at a PC version. It's kind of small, but this one, it tells you the type of processor. Doesn't detail out the cores. You probably have to drill down into that. But it does here provide the resolution for the monitor component. So 1366 by 768. So 1366 pixels across, 768 top to bottom. When you get to a more expensive version, you can see the resolution just jumps. So 1900 across, 1000 top to bottom. It looks like that's where they're maxing out resolution wise, at least in this line of PCs. And then the hard drive, we learned on Monday about solid state drives. We also learned about the NVMe method of storing data and how that is the fastest method. This hard drive is 128 bits of gigabits, sorry. It's very small if it's bits. 256 gigabits for the next higher one. And you can see we're going up to 512. Obviously, I think if I'm going to invest in a laptop and depending on how I'm going to use it, I'm going to want more space so I don't have to carry around an external hard drive. All right, and then this is going to be our RAM values here. So some of the concepts that we talked about in class represented in real life situations or real life scenarios. All right. Closing out the class, we're at the end of our journey this evening. Tell me how you will feel. Tell me how you feel about the class. So very complicated concepts. Like I said, if you want to chat about some of those concepts more, I can try to find other examples that may resonate better. And certainly don't be afraid to go out and search. You'll build on these concepts as you go through other classes. We see this terminology and these concepts repeated in all areas. Thanks, Melanie. All right, let's see how folks are feeling. Emphatic, feel great. Thank you. Love it. Oh, thanks, Henry. That's great. Thank you. Giovanni? Thanks, Allison. All right, if you guys are ready, you don't have any additional questions, feel free to disconnect. But if you do have questions, I'm going to stay on until there are none left. So fire away. Thanks, guys. You too.
So much.
Thank you. You're welcome. Any questions out there for folks sticking around? Thanks, Vic. All right, you guys, I'm going to disconnect. Again, I am on Slack if you have any things. Oh, okay. VC, you want to talk about the answer 255, 255 in respect of colors. How did you come about the number? So each color can be assigned a value from 0 to 255. And when you talk about binary numbers, you have a maximum combination of binary numbers up to 255. So when we're storing codes to represent colors, each color gets its own code value. So if the color is a, a smaller binary number, it's going to be a darker version of that color, because the closer you get to the, we'll say the decimal conversion of that binary color. Obviously, if it's if the decimal number is just 0, or the binary just represents 0, you're not going to have any value for that color. But if your binary number represents 255, you're going to have full color. And so that's why we have that range of 0 to 255 that we can assign for each color. Is that explained, or does that kind of leave you with still some questions? I'm putting the pyramid on the screen because the way I interpreted it visually is I was curious in terms of 1024 bytes, right? When you are thinking of the largest amount that you can store, the largest storage label that you can use, that's that terabyte, right? So when I think of size, think of a smaller amount up top, slightly larger amount, increasing amount at the bottom, the greatest amount, right? Don't be confused, because in pyramids they kind of build up with pyramids, and they say top is the greatest. But because this was a visual representation in size, and we were talking about size, that's why I was looking for our terabyte value at the bottom, your gigabyte value just below that, your megabyte value are just above, and then your megabyte value in the green, and then your kilobyte value in the blue. Yeah, but if you were thinking I was crazy and it should be opposite, it's not wrong. It's just kind of visually how I saw the size. Oh, okay, gotcha. Let's see if I can label the pyramid. I don't know if I can label it from my side. Let me do it this way. Let me just in Excel, where we have our sheets. The values for the pyramid are kilobyte, megabyte, gigabyte, terabyte. Because when you're thinking conceptually in the aspect of 1024 bytes, so for each one of these in increasing magnitude, this is 1024 bytes, and then this is going to be 1024 kilobytes represented. So bytes is represented with a B. Kilobytes is represented with a KB. Megabytes is represented with a MB. Gigabytes is a GB. So at the bottom, you have your largest size of bytes. Does that help, Nadia, or should I try something different? Yes, okay, great. You're welcome. Oh, great. Thank you. It's good to know. Thank you. Okay, anybody else? If not, good night. If not, I will see you on Saturday morning, 10 a.m. Eastern, where we will cover additional topics like software. Yeah, we're going to talk about it. I saw the entry in the Allison, if you are still on the call, we're going to talk about algorithms, machine assembly, high-level languages. So the components of software, kind of how software works with the different languages that we use to create it. All right, see you soon, guys. Have a great evening. And thank you so much for joining me.